All right. Before we get to Maxwell's equations, let's talk about Ampere's law again. So if you remember, Ampere's law basically said that if you have a current, right, it creates a magnetic field. The magnetic field goes in a loop around the wire, an imaginary loop, right? And so for a particular wire, if it if it's a straight wire, um, that magnetic field was uniform around a circle that would go around the wire. And so you can kind of imagine there's this space, this area, the surface that that loop creates. Now, technically, there's actually nothing about Ampere's law that says that that surface has to be flat. No matter how you draw your surface, so I know the color is a little harder to see. That's a little different, but I tried to use purple there. Let's say you have a different surface, surface 2, that is kind of bowed out. So the wire still goes through both surfaces. And so, according to Ampere's law, at the point, at the, the loop that we're interested in, that magnetic field is still the same. And again, if you're trying to figure out what that second surface looks like, think of it like a dome. And the edge of the dome is your loop, right? And so if your loop goes through the if your wire goes through your surface, or you have current going through your surface, essentially that current has to go through both surfaces, the surface created by your loops, unless the wire stops like partway through and turns around, or it just straight up stops. Right, so unless the wire stops, it must go through surface 2, or it has to turn around and go through surface 1. If it goes back through surface 1, then you have no net current through surface 1, and so you actually have no net current going through either surface. And so you still have um, the correct Ampere's law. No current going through either surface means no magnetic field through either surface. Well, let's look at a situation then if where the wire does stop. And a good example of this is, let's say you have a capacitor hooked up to a battery, right? And so once you close the switch, look at the bottom. Once you close the switch, there's a current that goes clockwise, and so that current is going to build up a charge on your capacitor. And if you zoom in on that capacitor, the right hand side is negatively charged, the left hand side is positively charged, and at the moment that it is charging up, positive charges leave the right hand side and enter into the left hand side. So you have kind of a net current, and that current is changing over time. Uh, but there is a current. It will right, and so again, since there's a current, we can draw this kind of imaginary circle, this imaginary loop around the wire, and investigate the surface. But let's look at two different surfaces. One surface where the wire literally goes through that surface, the left side of it, kind of like the bottom of that uh, the dome, the left side of that little round looking shape that I drew. The original surface, surface 1, right? And on the right hand side, or on and the other surface, surface 2, that loop or that surface kind of domes around the positive side of the capacitor through the center between the capacitors and back around, so that that surface doesn't actually have any wire going through it. Okay? Now the loop, um, is in the same spot. Okay, it's the circle around surface 1, and it is kind of the left edge of that dome of surface 2. So you can still say that that closed integral of that path BDS is the same for both, but there's only current going through surface 1. So how does that work? According to Ampere's law, that loop is the same for both, but one has current and the other does not. And according to Ampere's law, um, and the only way you can have magnetic field is if you have current going through um, your loop. And so, it's obvious that it's going through the loop through surface 1, but it really shouldn't matter which surface. And so, if we continue with this thought experiment, trying kind of just redraw this. Let's consider um, looking at this again a little closely right at the beginning. You close the loop, okay, and then you have charge, and you have current. The current, um, goes through, and it is, the fastest in the beginning, right? It's charging up in the beginning. So immediately, right in the beginning, that's really when you have um, not necessarily your strongest field. You have the most current, but not your strongest field, right? You get the strongest field when it builds up the most charge. So even though you have the most current in the beginning, you actually have zero charge in the beginning, and so therefore you get the most rate of change of charge buildup at the beginning. So your charge is building up in the beginning, and again, if we investigate this, these two surfaces, that surface number two is a surface that is experiencing electric flux, right? Because as the two sides of the capacitor build up charge, it starts to build up electric field between them, and so then you start building up a electric flux through that surface, not surface one, but surface two, right? The domed one that wraps around that left um, capacitor wall. So you look at the electric field from capacitor, it's just dependent on the charge in the area. And so since flux is also dependent on area, you see the areas cancel out. So the flux between your capacitor is really just dependent on the charge. And that charge is, of course, depending on the current, dependent on the current. So to relate that, if you just look at the rate of change of the flux, that's how you're going to get your rate of change of your charge, which is essentially your current. So the rate of change of your flux, your electric flux, is equal to your current divided by the permittivity of free space. Again, remember the current is not constant. It's biggest in the beginning, and it starts to die off. Right. Looking back at if you had an RC circuit, so to speak, except that it's charging up. So there's no physical current going through that surface. There's no physical current going between uh, the positive plate of the capacitor to the negative plate of the capacitor. But if you look at the equation, your rate of change of electric flux seems to be equal to some current, right? And so we'll call that a displacement current. And so basically what Maxwell found out, and Ampere, when he did his, it was for an actual current going through an actual wire. And when Maxwell investigated this, he found that a rate of change of electric flux can also, to a certain degree, imitate a current in the sense that it's creating this magnetic field. A rate of change of electric flux is creating this magnetic field. Remember, because that loop, the original loop, the left end of that dome, um, is the same. It's the same loop, right? And so either you have your current that's creating that magnetic field, or you can think of it as the changing electric field that's creating that current. So surface one, it's you can think of it as creating that the magnetic field through the current. But surface two is creating the same magnetic field through the changing electric field. Okay, so let's look back. Um, it's kind of interesting to compare the Ampere-Maxwell equation, right? This is the one where your changing electric field or current can create a magnetic field, and compare it to Faraday's law, because Faraday's law is kind of the opposite, right? It's the reverse. A changing magnetic field can give you an EMF or an electric field. So as I write these out, these two can be kind of tricky. They look similar, but they're different. The Ampere-Maxwell law tells you that changing E can create a B field. Changing electric fields create magnetic fields. Faraday's law is reverse. Changing B fields create electric fields. Now they're not exactly, um, whatever opposites of each other. They do behave slightly differently. especially in terms of the direction in which the fields are created. So for Faraday's law, we had Lenz's law to help us decide the direction of the electric field that is induced. We said that this induced field seems to oppose um, the changing magnetic field. So if you don't use the absolute values, oftentimes it's written with a negative, and what that negative is essentially codifying or mathematically representing Lenz's law. That electric field that's created is opposite from the changing magnetic field. So an increasing magnetic field seems to create a electric field that will try and oppose it, so to speak. Um, and we kind of did that with the induced flux, but maybe an easier way to look at it is really just try and memorize it like this. Let's say you have this magnetic field going into the page, drawing it with the red, and let's say that's increasing. So you have increasing field into the page, right? If you had, if you did the right hand rule and you stuck your thumb in the direction of B, um, you would have something that's in the direction of B, but it's not. It's negative, so it's the opposite. So you actually have an electric field that is in the opposite direction of B. So increasing B into the page, you end up with a curl or a induced E that is counterclockwise. That is, your thumb ends up pointing out of the page. That's where the negative comes in. If you look at the Ampere-Maxwell equation, though, both of those terms on the right-hand side are positive. Um, so that induced B is in the direction of E, so to speak. Um, when I say that, I don't mean like the B field is literally in the direction of E. I mean the way your right hand rule, your thumb ends up pointing, curls your fingers, around the current or around the increasing electric field. But your fingers curl in the direction of B as opposed to the opposite. So, for example, if you have, again, an electric field this time pointing into the page, an electric field pointing into the page, and if you have that electric field increasing in strength, okay, so your thumb, if it were to point into the page, is increasing, pointing towards increasing electric field. The direction your fingers curl is now curling in the direction of the induced magnetic field. Okay, so compare the left-hand side, compare the Ampere-Maxwell situation to the Faraday situation. The Ampere-Maxwell situation, for increasing E, if you point your thumb in the direction of increasing E, your induced B is in the direction of your fingers. Whereas for Faraday, it's the opposite. It's the opposite. Um, and again, that's kind of from Lenz's law. And yeah, I added a couple notes here, but I can't remember what exactly I said, and I did not slide it up. I think specifically for both of these cases, if you're looking in the direction of increasing, yeah, in the direction of increasing B or E. So again, think of it as if you point your thumb in the direction of the increasing B or E. For Ampere Maxwell, your fingers curl in the direction of E. For Faraday, your fingers curl in the other direction.